So we're going to present, I'm really excited to be presenting our work today on quick and quick deployment in front of you guys, and really excited about seeing the program that is currently on the docket. So since the beginning of standardization of quick, we've seen the quick protocol evolve quite significantly from what it was originally to adding new features that are required for deployment. At Facebook, we've been both implementing as well as deploying quick in various surfaces. For example, we've deployed quick on the internet as well as our backbone networks as well. And so what we've learned from these deployment schemes is that not only does quick change the fundamental abstractions and semantics of the transport protocol, but quick also changes certain way we build our infrastructure systems. The things we've grown to rely on in TCP don't exist in quick anymore. So in this presentation, I'll talk about some of the changes we've had to make in our infrastructure to support quick, which classically relied on TCP to work correctly. And I'll also talk about some of the results that we've actually seen from a public rollout of quick. And hopefully we can start a discussion. It's more like to start a discussion and kind of go from there and see what extra results are we should go and kind of aim for. So before I get into the details of what the infrastructure changes are, it would probably help to know what the Facebook infrastructure looks like, or the load balancing infrastructure looks like. So 100-foot overview of the Facebook load balancing infrastructure is we have a double load balancing infrastructure model. So it's very common in a lot of other CDNs and networks right now. So we have a load balancer which we build called Proxygen. And there are two layers of Proxygen load balancing. So one of the layers of Proxygen load balancing is at the edge. So this is usually closer to the user. So the edge load balancer Proxygen terminates the connection. And so by termination, I mean it terminates both the DLS as well as the TCP connection from the users and their phones. Then once it terminates the connection, it decides which upstream to send it to, which data center to send it to. And it forwards it to an origin load balancing service. So the origin load balancing service decides then to load balance between the application servers, which is, in this case, is HHVM, which is running PHP code, which decides what cat code is to render you. So when I'm talking about deployment of quick here, I'm actually talking about deployment of quick both in the internet from the mobile phones to our edge load balancers, as well as some deployment of quick from in our backbone network, which is our edge Proxygen to origin Proxygen load balancers. Another point is how are we able to deploy quick without browser support? So we actually control the mobile networking stack, both on the Android and iOS phones, as well as our own load balancer, and L7 and L3 load balancer. So side note that this is actually a cross-platform C++ library that we wrote, so it's actually the same code that's running on the mobile app that is running on the load balancer. And so we're able to deploy it really write once, run anywhere, and deploy this code really quickly and get tests. And so we have our own implementation called Move Fast, and that's why hence the title of the talk. So like I mentioned previously, there are a lot of things in our infrastructure that we've built over the years we've been running Facebook, which rely on TCP. It relies on the goodness of features of TCP that we've had so far. So for example, a few of the things I'm going to talk about in this presentation are, we want to be able to restart Proxygen without disrupting user connections and ruining user experience. We want to be able to route packets that enter our network in a stable way to the right load balancer that is supposed to handle, and right application servers that are supposed to handle those packets. On the client side, on the mobile apps, and on the load balancers which connect upstream, we want to be able to effectively pool and reuse connections that are going upstream to the load balancers. And lastly, we want to be able to instrument and debug crazy edge cases that happen in a very large-scale infrastructure environment and figure out why they're happening and solve them. So the first problem of zero downtime restarts. So the context around this problem is that we restart Proxygen all the time. So Proxygen restarts for several reasons. One of them is, for example, we want to run a canary to test a feature in production, or doing a binary update of the binary, which happens quite frequently. So when proxygen restarts, we can't just kill the old process and start up the new process. What that would mean was that it would disrupt all the connections that are currently pending on the process, because TCP connections are bound to the process at the moment. So, so usually the solution to this problem, the solution we adopt and some other CDNs also adopt, is let's keep the old proxygen instance alive for some amount of time, and then the new proxygen instance can handle new connections, and the old proxygen instance can handle existing connections. So a quick overview, if people haven't seen a system like this before, a quick overview of how this works, at least in proxygen's case with TCP, is so you have in the existing state, you have an old proxygen instance which is running with a bunch of accepted sockets which are distributed across threads. Each accepted socket corresponds to one FD, which is a client, a unique client that has established a TCP connection to us. And we have listening sockets as well, which are also distributed across threads. Those are accepting new connections from users as they create new connections as they come in. When we want to restart proxygen, a new proxygen instance starts up. The new proxygen instance decides that it wants to take over all the existing listening sockets from the old proxygen. So the way it does this is that it has an RPC protocol with the old proxygen, and then the old proxygen instance transfers all the sockets to the new proxygen over a Unix domain socket with a feature called SCM writes in Unix, which allows for transfer of the file descriptors in a C message structure. So this way, the new proxygen has control of the listening sockets and starts listening on the listening sockets, and the old proxygen instance stops listening on the listening sockets and pauses at that point. So what ends up naturally happening is that the accepted sockets, which are currently, the existing sockets are currently live with the old proxygen instance, and so they can keep continuing to serve existing requests and draining those requests as time goes on, whereas all the new connections, they go to the new proxygen instance. This works great, it works very naturally with TCP, and the fundamental reason for this is this nice separation between listening and accepted socket file descriptors, which you can take over. Now,
have you considered moving over the accepted connections? TCP repair or something like that?
So we have considered that, but it is actually way more complicated than we think as well. The only state associated with the connection is not just the kernel FD. Right. For example, there's HTTP state associated with the connection. There's you might be in the middle of execution of a rule or something like that. For example, we've talked about what if we move only idle connections? But what do we do about the HPAC table and all the stateful stuff that we have inside the connection, which is not just our kernel?
How long-lived are these connections? So how long would it, on average, take you to ramp down one instance and get up the new one?
So it takes about 15 minutes or so to ramp down all the old ones. So we're pretty aggressive. It depends. So in correction to that, it depends on the use case for the connection. For example, if it's a pure HTTP connect, we terminate lots of different kinds of requests. For example, we terminate long-lived messenger type of requests as well, like long polling requests. We terminate normal HTTP request responses as well. So it depends, and it's configured based on the use case. And so if it's appropriate messaging, requires a longer drain time, and then just normal HTTP is very short. We can drain immediately with go-aways. So you might have seen this coming, but there's a problem now we have with UDP. So there's no separation between listening and accepting sockets in UDP. So we can't just take over the listening sockets like we did for TCP in the case of UDP. So if we had to take over something, we would have to take over all the UDP sockets that are currently listening in the old process. So not great. What that means is that the old process will stop, cannot read any more packets from old connections, which is not desirable for us. We said that we wanted the old requests to be served by the old proxygen still. So one solution some people might come up with is why not SRE support? SRE support is a function that exists in the Linux kernel, which allows for packets to be distributed across sockets which exist even in maybe multiple processes. So there's a very slight edge case in SRE support with ePPF, which makes it unusable for this use case. For example, I don't want to get into details of that, but I'd be happy if anyone has a question. SRE support does not have a stably routing, doesn't stably route packets across FDs. when a connection dies, it just completely rearranges the FD table. And so it's not great for our use case at the moment. So our solution to this was, since we're a user space protocol, let's just solve this in user space without kernel's help at the moment. So at a high level, the solution to this is, our solution is, if the new proction receives packets, it will take over all the sockets from the old proction. If it receives packets which it knows are destined to the old proction, it just forwards them over as UDP packets in user space. So then the question comes in is, how does it decide whether a packet is meant for the new proction or the old proction? So we introduced this concept called process ID, which is not PID at all. It's just process ID for extra confusion. So the process ID is given, each proction assigns itself its own process ID. So the process ID can be either 0 or 1, because we know that we will only have 2 proctions restarting at any one point in time, so we don't want to support more than that. So every time a proction starts up, it chooses its process ID through some way. And whenever it creates a new connection to the client, it actually generates a server-chosen connection ID, uses a new quick feature which is introduced only in IDF quick. It doesn't exist in gquick. But it uses a feature called server-chosen connection ID to embed this process ID in every single connection ID it issues to the client. So what this means is that so looking at the right-hand side, you're right, you can see the PID bit is embedded inside the connection ID. So when the process receives a packet, it knows exactly, this is my PID, is this destined for me or the old proction instance? And it forwards it if its destination is it. We also have another feature that we'll get to in a minute. We also can do direct server return from the old proction instance with this model. So quickly illustrated as how this looks, how this all comes together, is let's say there's a user who has an existing connection, existing packets, sending existing packets to an old proction instance. The way our architecture works is that we have a bunch of UDP sockets which are all bound to the same SRE port group, which are distributed across threads, and they're all listening for new packets that are coming in from users. And associated with those UDP sockets, we also have quick connections as well, so they're abstracted away from the quick socket. So when a packet is received, we decide based on the information in the packet, for example, connection IDs, where to route the packet to, which quick connection should handle this packet. Let's say the new proction instance starts up. So there's an RPC mechanism. The new proction instance asks the old proction instance, what is your process ID? So if the old proction instance says 0, the new proction instance assigns itself a process ID of 1. So it just inverts it. If it said 1, it would just assign itself 0. So this way, we don't need any other inter-process communication to do this thing. Once the new process has a process ID that's associated with, it takes over all the UDP sockets from the old proction, using the same exact SCM rights mechanism that we mentioned before for TCP. When it does this, the old proction instance stops listening on the UDP sockets that it had, and actually instantiates a new set of sockets called takeover sockets. So takeover sockets are actually just bound to local hosts, so they are not routable to the public internet, but can only be routed by another process in the same host. So how the takeover sockets are used is, let's say the new proction instance receives a packet from a user and a UDP packet from a user. Based on the process ID and the connection ID that it assigned, it decides whether or not the old proction or new proction should handle this packet. And when it does decide that the old proction should handle this packet, it forwards it to the old proction to the takeover sockets that are bound at the moment. And it does this after encapsulating it in its own UDP datagram packet. So the encapsulation allows us to supply things like version number and also the original source address that are associated with the packet.
When you say encapsulate, do you mean you NAT? You rewrite the IP?
No, we don't rewrite. We just put another packet on top of it.
So you put an IP, so it's not a UDP packet.
It's a UDP packet. It's a UDP inside a UDP packet. We do UDP encapsulation.
But no IP, okay.
No IP. Yeah, it's UDP and top UDP encapsulation. Okay. It's easier that way. We don't need raw socket. We don't need raw access or anything like that. It's just normal. And so when the takeover socket receives this encapsulated UDP packet on this port, it knows that this port can only handle UDP encapsulated packets. It knows the version of the encapsulation. it can then decide, I want to decapsulate this packet and treat this as if it was from this source IP address and handle it normally as it would regular connections. It doesn't need any change to the connection state machine logic to handle encapsulated packets, which is a nice feature.
If you're not using raw sockets, how do you then get the original or source IP in there? Is this part of your encapsulation?
So read will give you the source IP in the. So we actually we get the source IP from UDP itself,
right,
like normal. Yeah.
But how do you read? Well, so this is encapsulated at the UDP layer.
Exactly. So we encapsulate it at the UDP layer, and then so we're able to get the source IP from the encapsulation. Yeah. So we can make all these. It's required for all the security purposes. Like we don't want amplification vectors and stuff to happen, so we have to do these things. The nice feature about this is that once we get rid of the old connection, it's just gone. Once we get rid of the old proxy, it's just gone. We don't need to worry about it anymore. So the other feature about this mechanism is that we're able to direct server return from the old proxy instance as well. So when I mentioned we take over the UDP sockets from the old proxy from the new proxy instance from the old one, we actually only take over the read side. We actually keep the write side of the sockets in the quick connections embedded in the quick connections. So when it wants to respond, which is sometimes the larger data path, we actually just respond directly to the client. We don't need to go back through proxy. It simplifies the architecture. It also naturally falls out of this, so it really helps.
How much overhead do you add in terms of time? I mean, you encapsulate a packet in another packet, and I imagine you process billions, millions of packets.
So it's not very significant. We haven't seen any significant regressions in CPU, for instance, and time. Like there's no real difference in time that we noticed, at least. So another thing we do in the encapsulation, we also embed the original packet send time that was that receive time that we received it at for ACK processing. So we can then compute ACK delay in an accurate manner. Like we can treat that as a part of like this didn't exist and this was just encapsulation delay. So we haven't really noticed it in terms of this. And Quick can compensate for those delays if those exist. And those connections are going away anyway, so it doesn't really matter. Like honestly, it just needs to exist, not get dropped. It's good. Any other questions? Awesome. So how well does this work in practice? Okay, it sounds great, but how well does it work?
It's invisible.
Is it usable?
No, it's
invisible.
Oh, it's invisible. Oh, I see. It's invisible.
Secret results.
I used stenography. I'm sorry about the projection, but you can see, kind of make out the fade outline of the left-hand side shows packets forwarded during restart, so that usually corresponds to restart events that happen during proxy. So forward means that we decided that this packet was destined for an old proxy instance, and we forwarded to an old proxy instance. And so you see the spikes are usually restarts. And you can see the packet on the right-hand side shows the number of packets we dropped during the restart in total. It doesn't move a blip. It just normally follows the normal traffic pattern, which is like it was decreasing at this time. So it works pretty well. This matches the results we see with TCP as well, and so we're pretty happy with this mechanism. But the problem is that like if you have a regular implementation, like this is madness. Why would you forward things? Why doesn't the kernel actually provide better support? Linux kernel provide better support for this? Well, it's coming. So in a 4.19 kernel near you. So one of our kernel engineers, to address this problem, has actually committed a patch to Linux to allow for an exposure of a new eBPF map array type called eBPF as a reuse port sock array. So this will actually allow you to stably route packets and also do things where you don't need to do this forwarding anymore in user space. You can actually just let the kernel forward it based on the process ID. You would still need to embed something like the process ID in the server chosen connection ID, but now the kernel will take care of using the eBPF program, which should be fairly common amongst all implementations. You can forward packets across different processes. So depending on which kernel you're targeting, if you're targeting 4.19, then this is great, use this feature. If you're targeting anything lower than that, then you might have to come up with some solution which is user space forwarding. Thanks. So another problem with we saw with Quick versus TCP, and what we've come to rely on with TCP is actually stable routing of packets to our infrastructure. There's several layers of routing inside the Facebook infrastructure and generally in complex networks. So we want to make sure that packets get there in a reasonable manner and to the right place it was destined to. So in TCP, this is great. We have this infrastructure in TCP, a connection associated with 5-tuple, but in QUIC, a connection can be associated not just with the 5-tuple, and the 5-tuple can change. We want to make sure we can get the packets there to the right place, even if the 5-tuple changes. So when we first rolled out QUIC on our backbone networks, we actually started seeing a huge percentage of timeouts, which were disproportionate to the amount of rollout that we saw. So we investigated this as a engineering debugging exercise, and we first suspected that they were dead connections. So the client is sending us packets and the server is actually idle timed out the connection, in which case QUIC does not send the connection close to the peer to avoid radio battery wake up problems. And so we just kill the connection and the client is sending packets to a dead server and it keeps absorbing the packets. At the times, QUIC has a feature called stateless resets. So it's similar to a TCP reset, but it has more authentication for on-path authentication associated with it. So at the time, we had not implemented stateless reset yet because we thought it was an optional feature. So we decided, okay, if it is dead connections, we should probably implement stateless resets and we should implement it. So when we implemented stateless resets, we saw, yes, the timeouts went away, but they were replaced with worse errors. That is, all the connections were getting reset, and the error rate was actually much higher than the error rate of timeouts that we're seeing. So there must be something else going around. So we first suspect that the next suspicion that we had was that it might be misrouting of packets on the wire. But since there's so many layers of routing, it's really hard to diagnose and even harder to prove where the misrouting happened. So to actually address this problem, we used one of the core features of QUIC again, which is a server-chosen connection ID. So this is a theme. Promise is the last slide associated with the theme. But so let's debug this thing using server-chosen connection ID. So we assigned in our infrastructure all the hosts unique server ID, and then when we're generating a connection ID for that host, we embed the server ID into the connection ID that was generated. Then when we receive a packet from the client and we notice that the server-chosen connection ID does not match the connection ID that we expect, the server ID that we expect the server to have, we said that something has gone wrong. This is a misrouting failure, drop the packet and log it. So using this mechanism, we were actually able to drill down and see that it was actually happening at a cluster level, and it was actually a problem with the misconfigured timeout for the, basically we have a LRU cache for connections, and so timeout for the LRU cache was very low, and we weren't setting it to be the same amount of timeout that we were setting for TCP as well. And so as a result of which, the binding was getting broken, the routing binding was getting broken to stably route it to the right server, and as a result, we were dropping packets on the floor like crazy, and that was resulting in timeout. So packets would come in and just disappear somewhere. Okay, that's not great. So we decided to go one step further. This idea worked so well that we decided to go one step further, and we decided to implement server ID based routing inside our L3 load balancer. So we could do this because we actually own our own L3 load balancer as well. It's an open source project called Katran, and it actually right now has support for quick server chosen connection ID routing. So if you're in the market for a load balancer, L3 load balancer, it's great. You can see on the right-hand side of the graph of before we implemented server-chosen connection ID support inside the L3 load balancer, and after we implemented server-chosen connection ID support in the load balancer. Hopefully this red line should be more clear. The packet misrouting just went down to 0 from like a higher number. I can't actually reveal the exact numbers, but you can see that it was a dramatic decrease. So the other thing that we saw was that we can actually do better than TCP in QUIC. In TCP, we have to maintain an LRU cache. We have to maintain some state associated with the consistent hashing for some amount of time, because servers in a backend load balancer pool can change all the time. So either you do consistent hashing, or you hope that the consistent hashing, when you have 5-tuple, you hope that it goes to the same server again, and so you maintain some amount of state for some amount of time. However, with QUIC, we didn't need that state at all. So we can actually do better with connection ID routing and routing inside of load balancers so quick than we can do in TCP. And it's not an accident, it was designed this way. And we helped in designing this way as well. So we're actually planning to use this in the future for other misrouting cases, and which might be helpful. For example, in multipath cases, when the IP address will change, we want to route back to the same server. We can't use anything other than server-chosen connection ID routing. In any cast use cases where we might end up in the wrong cluster, wrong region in itself, like in a P99 percentile of the case, we want to route back to the same cluster. So we plan to use this everywhere. And so it's going to become a big thing. You heard it here first. Now that we solved the connection ID routing problem with hosts, now that the misroutings are down to 0, let's explore resets again. So we still suspected that even after the misrouting happened, that we had a problem with dropping packets that were being sent after the server idle timed out that connection. So we decided to implement resets after we did this, and we actually saw an insane reduction, like 15% reduction in request latency after implementing resets with no change in errors. So resets and connection ID routing work very well hand in hand, and it makes sense. It makes obvious sense as well. Any questions? So we've been talking about some of the server side. I have a dog photo. I promised someone a cat photo, but I didn't. So we've been talking about most of the server side infrastructure, but we also have a very large client deployment as well. For example, both in our mobile applications as well as our edge-to-origin traffic that we're sending upstream. So connection pooling is really important, and unlike TCP, we can't just assume you can establish a connection and you'll have a UDP connection alive. So not all networks do allow UDP. For example, we've been in talks with networks which definitely block UDP, and as a rule. So I looked at the quick scan of some data that we had out of some 25,000 networks. We had 4,000 networks which have no samples of quick usage at all. So of course this looks really bad. It's like 16% if you do the math, but it looks really bad. It's actually not as bad because those 4,000 networks are all in the tail. So there's a huge tail population which doesn't allow UDP, but so it's not really important in the grand scheme of things, but we still have to support the cases where UDP does not work on the network. So we have to do something to race Quick and TCP together to see which one wins. So over time, we actually evolved our racing algorithm to get better over time. And hopefully, I'll walk you through, the next few slides will walk you through the evolution of our racing algorithm. And hopefully I'll convince you that racing is a non-trivial problem to solve.
For these 4K carriers, have you talked to some of them? Is it an accident or is it deliberate? Or?
No, it's some of them are deliberate. They are deliberately blocking, but some of them are working on turning it back on again, but they're waiting to run a few experiments, and some of them no response.
Why I did that? What's the reasoning?
We were just told it was blocked. No, sorry.
Just curious, since you're talking about racing, are you also racing V4 versus V6?
I'll get to that in a minute. Oh, sorry, go ahead.
So they're all grouped in a tail network? I didn't understand.
Oh, they were all in the tail, as in like there are not that many samples, so there's not that many statistically significant samples of data from these networks that block UDP. So it's the number for one part, it's hard to group by carrier because we have various heuristics to decide what is a carrier, but there's a lot more problematic things around it's an MVNO, is it like, there's a lot of stuff which is means carrier, which it's hard to decide what is a carrier. But apart from the data, we see I'll show you some more data which says that this is not as much of a problem. So the first iteration of our approach was a naive algorithm. Well, I call it naive because we have a better algorithm now. But when I'm talking about racing here, I'm talking about specifically racing TLS 1.30 RTT versus Quick 1 RTT. So it's actually the same number of round trips. So that's very important. So it's the same number important. So usually connection establishment is a very complicated process. You have to do like all this other stuff like V6, V4. You have to do proxy establishment, DNS resolution. So usually when an implementation, what we decided to do in implementation originally was the connection pool and the connection establishment are two modules And the connection pool asks the connection establishment layer, give me a connection, I don't care, just give me one connection, I'll put it in my pool. Great. So we didn't want to break this module first, so we decided to implement a naive solution where we just replace this connection establishment module with something that starts off quick and TCP both at the same time. So what ends up happening is that we can only return one connection to the response. So what we decided to do was if TCP wins, cancel quick. If quick wins, cancel TCP. Seems obvious? Great. So, and if both error, it's the connection error. The problem is we saw a dismal usage rate. By usage rate, I mean that quick is used for the request that is being sent out by the applications. So we saw about a 70% usage rate of quick, which is much lower than what we expected, really. So we looked at the causes for this. So some of the causes for this, we saw a lot of probabilistic loss events. So quick and TCP both have the same number of round trips. So it's 50, like if you just look at a raw probability, it's 50% chances that quick will definitely lose it. Both the request patterns are all uniform and requests are always being sent in the clear. Request patterns are not exactly uniform, so you see like a little bit higher number, like 70. We also see some TCP middle boxes on the internet which speed up TCP. We also see some weird errors that we see on the quick only on UDP and not on TCP on Android. For example, we get eNAT unreachable on UDP only, but not TCPs. It might be networks where UDP is blocked. We're not really sure what the cases are, but 70% is bad, so we need to do something better. So our next iteration of the algorithm, let's just give quick a head start. Like this probabilistic loss thing, let's like look away and then say that this didn't happen. So we just give quick a 100 millisecond head start. And start the TCP connection, and same thing, cancel the quick connection, TCP comes back first, and vice versa. However, we saw that this didn't really improve quick usage rate. So this is disappointing, but we suspect that there might not be enough time for radio to wake up and send the packet, and so that might end up, most of the time when we establish a new connection, we are in a state where we're waking up from idle. We're also seeing random, another interesting fact was that we were also seeing random losses of quick versus TCP, even with this 100 millisecond timeout, in the cases where UDP is allowed in the networks. We know that UDP works in these networks, and we know same ASN, UDP works in these networks, we see quick losing to TCP. It's like, okay, why? Okay. What we decided was let's just turn the model on its head. This whole racing thing of establishing one connection is not really working. So instead of trying to figure this out, let's just allow both to return successfully. So we just ripped apart the interface and changed it completely. So let's allow quick and TCP to run at the same time. If TCP comes back, great. Allow TCP to satisfy the requests that are currently outstanding. If new requests come out and quick has come back by that time, use quick for those requests and send them out immediately. So this involved like a crazy number of changes to the connection pool. It's really complicated right now, but it worked. Like usage rate was at 93%. Another thing we found that helped was we delayed the TCP connection establishment by 100 milliseconds, similar to previously. But what we do is if we see quick erroring out, we remove that delay so that we don't end up in a persistent like kind of loop where we always add the 100 millisecond delay when we know that quick might never work. But if we see quick being successful, we say it might be due to random loss. We add back the delay again. So even now we see random. So now, even though with 93% usage rate of quick, we still see random losses of quick versus TCP. We're not really sure why, and it is a good question to everyone to try to figure it out.
So this is random loss that you see at the start of a connection, or do you persistently see higher random loss for UDP even after this?
No, we see even in a single session, when we establish a new UDP connection, sometimes quick will win, sometimes TCP will win, and even with this whole like timer.
No, what I mean, so the random loss you see for UDP that causes you to do this 100 millisecond thing, is this persistent or is this only at the beginning of the connection?
Oh, all of this is only the beginning of the connection.
Right, but have you looked into whether this UDP loss is is it always higher than for TCP?
So no, it's not.
It's only
at the beginning of the, only when we start off, especially because this is a highly vulnerable time in the life of a connection child. The connection is just starting to like establish, and you're going to send all the requests. looking at that data is harder. So by losses, I mean not UDP. It could be UDP packet losses. I'm not entirely sure it's UDP packet losses, but it could be just delay. Sorry.
Have you spoken to the people doing stun and connection racing for real-time traffic?
I haven't, but that would be very.
They've got a lot of experience with racing UDP packets.
That's a good point.
They see similar effects.
Yeah, that'd be great. If you know anyone, then I'd be happy to chat with them.
Talk to them about TCP.
Fantastic. I will do that.
I was curious about, did you see any endpoint specifics? I don't know, Android version versus iOS versus something else?
No, it's just general. It happens in iOS, it happens in Android, it happens all across the board. It's pretty consistent, yeah.
All right.
So when racing in TLS TCP, do you control the underlying IP layer protocol? Because it seems like IPv6 has more packet loss.
Yeah, so we do. I'll get to that in the happy eyeballs in a minute, but we don't control. So we, as in controlled by, I mean. So first I thought you meant controlled by, as in do we control IP? No, we don't control IP. But even looking at both AFINet and AFINet 6, we see similar pattern as well. So grouping by that, it's exactly the same pattern. So we're still. Some theories involve like maybe quick loses to TCP and quick loses to TCP when the network is really bad for some reason. Like we see grouping, it's very highly inconsistent, but don't take me on my word. RTTs are generally higher when we do when we lose the race, but it's not clear that it's not consistently higher. So that's my point. It's definitely not an RTT thing. It's just probably probabilistic loss for losing there. So for example, another way to do this would be we could modify our loss algorithm to take this into account and say, just keep trying quick. Just don't we know this network, so if we could know the network that quick UDP worked on and UDP didn't work on, then we could hard code those networks and say, in these networks, just never try TCP. Just keep doing quick. And we could, if they had the Oracle, then we could do that. Or we don't have to race even. So what this suggests is that quick will work eventually. You just have to try harder. Yeah. So.
Just a quick follow-up. When you said that you're not really sure if these are UDP packet losses, could be just delays. That particular part, it looks like you could easily test it out, right? Given you have TCP and quick, you could mix and match and then see if it is just a delay that you're seeing in UDP or is it really a loss. Do you have any comments on that?
So I think so. If we put the quick delay afterwards, it will definitely lose. If we delay quick, it will definitely lose. If we delay TCP, then we kind of don't lose sometimes, 93% of the time. So we are collecting more data as time goes on, and so I'll talk about some of the instrumentation stuff, but it's still an open question, and this is still a problem that's unsolved, and it would be great to solve this problem in the future. Yeah.
So is the duration of this delay chosen arbitrarily, those 100 milliseconds, or?
It's based on some RTT is 50 milliseconds, and then just just add a bunch more, and then it's arbitrary. Pretty much, yeah. It's a static constant which is arbitrary. It's not great either, but it's fine. It's not, yeah. Okay. What about zero RTT? I didn't talk about zero RTT. What happens with So zero RTT is different because you don't have a chance to test the network before you send the zero RTT data, unlike one RTT. So we have a choice to make if we have a connection with zero RTT data pending and a TCP connection establishes and succeeds, we have a choice to make at that point. What do we do? Do we continue trying the zero RTT connection, or do we give up and retry? So we do the conservative thing, we give up. And what we do is fairly complicated, but we cancel all the requests that were outstanding on the zero RTT connection, assuming that they will never come back, and we replay all of them over the TCP connection. And presumably, because they're all replay safe, this should be safe to do in a security perspective as well. We only say in replay safe requests over the zero RTT connection at all. So we are still experimenting with this. This is still a work in progress, but we see this works pretty well in practice, we think. There's definitely alternate models that we can explore, but this seems to work as well.
Is it necessary once the TCP connection receives the zero
I'm sorry, could you repeat that again?
Why is it necessary to replay the request? I assume if the app races connections, it will send the same type of zero RTT data on both connections.
So that's another way. So the app has already sent the request. So the thing is, when you're racing zero RTT TCP and zero RTT quick, what ends up happening is the zero RTT quick connection establishes immediately. There's only local CPU delay. There's no network delay. So what ends up happening is that connection is ready to send requests on and replay safe requests on. So you've already sent those requests in the wire. Meanwhile, the TCP connection is still pending. And so when the TCP connection comes back and succeeds, we have to decide, do we give up on this quick connection? So what is happening to the zero RTT quick connection? Did it not succeed because it was due to random delay? Or what do we do with that data that's already sending out a request? So what we do...
From the client perspective.
From the client perspective, yes. Exactly. So this is from the client, what do we do? And so we just replay them. It's very complicated, but it kind of works-ish. So what about happy eyeballs? This is another thing. So when we're racing TCP and quick, we're racing TCP. No, actually racing TCP v4, v6, quick v4, v6. It gets really complicated to actually do all these races and for the application to open up so many connections and do this stuff. So we actually didn't want, there are some better properties that we have for not opening up multiple connections. So normally how you do this in TCP is that you open up connection 1 and connection 2 and then wait for which one comes back. But in Quick we can do better. So what we did was we implement happy eyeballs as a native feature in Move Fast. So you just supply the new IP addresses and just does happy eyeballs for you automatically. So the nice part about this is that the key idea that allows us to do this is we actually treat happy eyeballs as a loss recovery timer. So instead of treating happy eyeballs as like another process completely, we just say, if you're doing happy eyeballs, just set a 150 millisecond loss timer. And that's the happy eyeballs timer. And when the 150 milliseconds fire, treat it as normal loss and just try again on V4 and V6. So the nice part about this is that the same logic works for 0 RTT, 1 RTT, everything. You don't have to do anything special to replay requests across connections for 0 RTT. It just works because it's all part of one logical connection. And in the server side, if we decide to do like V4 and V6 are terminated on the same exact server instance, the same quick connection shared between V4 and V6, we actually have better properties as well because we can, if you do V4 and V6 and replay the 0 RTT data on both, you actually don't forward that data to the backend application server at all. You just deduplicate it inside the server itself. This is nicer if they both share the same client connection ID, same server chosen connection, same parameters as well, and the same client hello. It kind of falls out of this. So we'd recommend doing this. It works really well. The V6 usage rate we see is exactly the same as TCP, and we've tuned that for several years now, and this works pretty well in practice. Question?
I have a question for you. All these algorithms, they're really interesting. Did you see any entanglements of these algorithms with connection migration?
So we haven't implemented connection migration yet. So that is something that is a follow-up work that we definitely want to do. So what we do at the moment is that if you migrate a connection, we just shut down your connection. So what we see in practice, though, is without connection migration, so this data is not banned, the thing, but what we see in practice is if you don't do connection migration, for normal HTTP requests and responses, given our timeout on the server side for the HTTP requests and responses, the number of times you change your IP address, if your idle timeout is fairly low, which it is for us, is insignificant compared to this. So if you do connection, so we don't have a need to do like IP address migration at the moment without actively doing connection migration on the client. Eventually we will do connection migration on the client. That's slated for maybe next year or something. I'll probably look into that, yeah. So yes, this long answer to short questions, yes, there are a lot of entanglements and we'll have to unentangle everything again and reevaluate all these algorithms again when we do connection migration. And hopefully these ones should just work, and that's fine. Because these are all algorithms during connection setup time, so they're fairly independent from algorithms during steady state connection time, which is like when you really want the connection migration to kick in. Yeah, but I will have more results for you when I do.
Yeah, I feel that's a complicated problem because
right.
there are just so many cases to encompass in that.
Yeah,
situation.
I completely agree. It's like, what happens if you migrate connection during connection setup?
Yeah,
I don't know. I'll find out. Yeah, that's great. So I know that Rob is going to talk about this a bit later, but so another major problem we have with Quick that we don't have with TCP is the debugging tools. Where are the debugging tools? Hopefully somebody will show them to me. So as a quick interim to debugging these traces, we actually built a system for logging called QuickTrace. So QuickTrace is a bunch of things. So one is an API for logging from our MoveFast implementation. So it's actually, the objective is to make it very simple to log events that happen during a connection. So the model is that when an event happens, you log it, and then that event, and the other part of the system is that that event goes and gets stored in a dataset and sampled consistently across all connections. So we wanted it to be schemaless because we wanted to just like add logging wherever the hell we wanted and not worry about basically like adding a bunch of schemas that would slow us down eventually in the future. So in the future we're exploring maybe adding a schema for a certain set of logging to make it more efficient, but for now it's all schemaless. For example, on the right you can see maybe see a blur of what the quick trace looks like. So you can see, for example, there's several events in there. So you'll see cubic ACK. So we're using cubic, and every time an ACK comes back, we will log it, and we'll see, hey, look, this is your CWIN at that time. So the nice part about this kind of data, which differentiates it, and I think this is part of the theme where Quick can make things better for debugging, is that this can tell you why your transport took a certain thing rather than what it did. Like TCP dump, I feel like answers the question what it did, and the question of why is missing. So this kind of data will answer your questions, those kind of questions for you. So the other thing we wanted is to add request level logging as well. So we wanted logging from multiple layers into one thing. So you can see, if you can see this data set, you can see not only the cubic ACK events exist there, but also you can see on headers, on EOM, those all come from HTTP level logs. So we have this merge of logs from multiple data sources, and we can actually log this stuff. So when we see a problem in production, so we see the request production has a request level table. We see, oh, bad stuff happened. What happened? Okay, let's go join that table with the quick trace table by connection ID. Go look up the exact connection. So we sample by connection. So if you have a connection, you will have all the requests in that connection. Nothing short of all the events that happen in the connection. So we can answer interesting questions like what happened around that stream ID? Like, did that stream ID get affected by things like, did it slow down because it didn't have flow control? Did it slow down because it didn't have CWIN updates? So how long did the loss recovery take in the transport itself? So we've been actually able to debug a bunch of problems this way and find some interesting cases spelunking through quick trace logs. For instance, one interesting case we found with quick trace logs, which probably could use some fixing in the transport documents, is ACK threshold is not enough for recovery a lot of the time. So ACK threshold assumes that you're sending a bunch of data down the pipe and you're going to get ACKs in a timely manner for all that data. But actually, request patterns don't look like the idealized version of like somebody who's designed a loss recovery scheme. We see several times what happens is HTTP connections are idle most of the time, and requests and responses come in staggered into the load balancer. And since they go to the application server, that also has processing delay, and they come back staggered as well. So you're sitting in the middle, and you're seeing request staggered and response staggered. For example, this is a case that we found in the quick trace logs where there's one request and there's a response coming back, and that gets lost. That packet gets lost. Then there's another request, like maybe one RTT later, just before the TLP timer fires, there's another request, and that comes back, the response comes back as well. So the way that Quick's loss recovery works is that whenever a new packet is sent, it resets the TLP timer forward. So every single day, you see multiple sort of events like this which keep driving the TLP timer forward, where what ends up happening is that 4 RTT later, you don't have a loss recovery mechanism for the first packet that was lost. But actually you have to rely on fast retransmit, which is really not fast. In this case, 4RT is not fast retransmit, just rename it to something like slow retransmit or something like that in this case. But so there's a PR that fixes this potentially, and we have to try it out. But basically we should merge both act threshold-based recovery and timer-based recovery together and do them both together, and that would be a nice thing to do. And we can look at this data with the quick trace logs. Questions? Great. Okay, this is the interesting part now, maybe. So far we've deployed Move Fast on our load balancers and our mobile apps, and so we're actually running Quick Draft 9. So why Draft 9? We've been running it for a few months now, and Draft 17 is quite new. So it's good to get a baseline on how the new major changes to crypto acts and crypto streams have actually affected the transport. So one of the reasons we're running this is to get a good baseline. It also is like something we have. HTTP1, we're running HTTP 1.1 over Quick, which is, you can think of it like one HTTP stream per, one HTTP request response per Quick stream. So we also have an HTTP 3 experiment going on, but that's not as mature as this experiment. So I'm going to discuss this experiment right now. For congestion controllers, and this is one RTD. We're not doing 0 RTD yet. This is one RTD experiment. We're running QBEC as a congestion controller. The type of requests and responses that we're sending are mostly API, so it's not CDN requests and responses. So it's an interesting different use case as well. Very important, for example, this is a thing that loads your feed. It's an important request and response. And the requests and responses are fairly small. So it's like in the range of 64, 1K, 2K like requests and responses. It can go up to like 10K, 20K, 30K. It varies, but you can see it's smaller than normal. So where we do the test between Quick and, so we're running this experiment between TCTL's 130 RTT versus Quick 1 RTT. Same number of round trips, should not affect the connection setup time, should not be affected. And we see 99% of the cases in the test group, we actually see 0 RTT is attempted. So we're actually really testing 0 RTT. The way we run this is we run an alpha beta test. So to be specific, we're actually running not alpha beta on the connections or anything like that. We're actually separating users out into two different groups. So one of them is you get Quick, and one of them is you don't get Quick experiment. So it's actually completely independent samples, and the same user will not get both Quick and TCP unless they fall back to TCP using the racing logic. Questions about the experiment setup?
This is your RTT timeout. Like you have a window in which you accept 0 RTT.
I'm not sure what you were talking about the LS13 or
tickets expired.
Oh, tickets expired. We set it to less than a day. Yeah. So we persistently cache tickets. We do a bunch of optimizations there to persistently cache tickets and like renew tickets. But it in practice, like the request response pattern, people are pretty engaged. So they're like, okay, they come back quite often, and we see a high usage rate of 0 RTT. Really. Okay. Let's move on to the results. Before I explain the results that on the table, like this table is kind of confusing, but unfortunately that's the case. The case with all results, right? So on the left-hand side, there's several different data cases that we've seen. And the right-hand side is the P's stand for percentiles, the 75th percentile, 90th percentile, and the 99th percentile. And each cell represents a percentage improvement we see in the metric that we most care about, that is request latency, request and response latency. Further down is better, further negative is better. That you can think of it. So you can see for the overall latency number, basically there's this insane dramatic shift in P 99th percentile to 23% improvement. So it's like insane. We find it hard to believe. We can actually validate with other numbers that it's probably real. Probably. So so we wanted to see like where is this insane number coming from? Is it like congestion control? Or are we like very aggressive in congestion control or something else? So we controlled by like, let's say we send very small responses, only for responses less than 4K. We still see a dramatic improvement in 99th percentile, so it's really good. So it suggests that maybe it's some other mechanism. Maybe loss recovery is the one. It's very hard to tease these mechanisms apart and kind of get the root of the cause of the matter. Then we also analyzed, for instance, what happens in reused connections only, not new connections, not established connections, just reused connections only. We see a smaller improvement in P75, 75th percentile, but we still see a dramatic improvement in P99. So, like, this sounds great and all that, dandy, but there's still like this giant elephant in the room, which is like, what if there is bias in this experiment? So we've have other data sets to correlate that it's helping, Quick is helping, and what if there is bias in this experiment because of we have 93% of Quick usage rate, but that 7% is still using TCP. Why is it using TCP? For instance, maybe it's a higher RTT, that's because we're using TCP. Maybe it's some other reason we're using TCP that we don't know of, and that's biasing the experiment. So we're always very worried about this, and we try to like control for this data. So the control for this data, we actually like put up two numbers. One of them is what about later requests and responses? They should not be influenced by connections out of time at all. Let's take them into consideration. So we see a smaller improvement in P99, but it's still pretty significant. For example, improvement in it's a good number to have, and smaller improvements in P75th percentile. Of course, this is like not a perfect way to correct bias, but it's something that we have. And then we also control for the same later requests, like maybe 10, 15 requests down the pipe. What RTT should be fairly stable, maybe. Let's look at like latency for connections which have lower RTT. So this is actually, all this data is viewed from the client-side perspective. So it's actually not server-side logs, so it's actually what the latency the client is seeing for establishment. So similar numbers as well. So we think that Quick is helping us, and the loss recovery mechanisms are driving this, the 99th percentile of improvements in the latency, request latency.
Couldn't you get your bias out if you don't do what you're currently doing and splitting the users, but having each connection flip between A and B, and then you take out those that never chose Quick?
I think there's still bias in that experiment, because if you don't consider the process by which you actually you select Quick or TCP, then there's still bias. Like for example, let's say that the connection never works for that user, then that's also like not a great thing. There's definitely, I think the process matters. So getting the root cause of why connections are randomly falling back to TCP is like very important here, and we need to study that more in detail. Sorry, anyone? Questions?
What about unsuccessful requests?
I can pull up the number, but so the error rate is pretty consistent, and unsuccessful requests we actually see pretty much the same latency. So there's no change in that. Sorry.
I'm sorry if this question appears a bit not well formed. Your quoting percentages, I mean, great. I mean, I can see some numbers and all that, but what does your absolute numbers distribution look like?
I wish I could share that. These are, I can say that these are significant numbers, for instance, and so maybe in the future I will be able to share that, but these are significantly improved. Yeah.
So these latency reductions, first of all, they are compared to TLS TCP, right?
Exactly, yeah.
And this is after happy eyeballs or connection racing.
After happy eyeballs connection
racing. Because if I looked at the previous slides, you also mentioned that if you give 150 milliseconds head start to Quick, sometimes, many a times TLS TCP was still winning.
Right, yes.
So it was faster than Quick.
I think it matters what the process is. I don't think it's faster than Quick. We just saw that Quick lost. I don't think that the connection establishment was, I don't think it's accurate to say that the connection establishment was faster than Quick. For some reason, it was lost. So it's not that TCP is faster on this network than Quick. It's just like, in that instance, it lost. 7% of the time in that instance, it lost the race, yeah.
So does it make sense to look at these numbers before happy eyeballs or racing, and then apply those numbers to the racing algorithm? Based on the empirical data, okay, this is the timer value I should use based on the advancement that I have seen with connection improvement of Quick to TLS TCP.
So by that I mean, so we can follow up about this, but I'm unsure what you mean by looking at the numbers before happy eyeballs. Maybe are you suggesting just fixing on one AF like address family and then doing that only, or are you suggesting doing something different? I'm not entirely sure. Oh yeah, sure, yeah. Okay, awesome. The initial numbers that we have are very encouraging. But there's clearly a lot of future experimentation needed, and we're open to seeing what kind of data would actually be people interested in looking at. Since we have Quick Trace, we can have a lot more finer-grained data about the connection the intricacies of the connection establishment and connection, the connection state, you might say. So we can tell you what the sea wind is, what the cubic congestion control, how much loss is there, like all this other stuff. And so a lot more experimentation is needed, but we can get a lot of this data. And if people are interested, we'd love to work together about this. So the other takeaway is that not only does Quick change the transfer protocol itself, but there's a bunch of infrastructure changes needed to support Quick as well. So when you're looking at evaluating, whether or not I should use Quick, then this is something to keep in mind, that all these infrastructure changes might affect the transfer protocol decisions or the optimizations that you're kind of proposing, whether it works with these infrastructure changes as well or not. So we've done this work so far, but there's several other things that we are currently exploring. One of the things is draft 17 support, so we want to make sure we do an A/B test of whether draft 17 still has the same wins that we saw in draft 9. So draft 17, for context, changes a bunch of other things in the transport protocol semantics, because it has separate ACK spaces and all these other things. Zero RTT, we're running an experiment at the moment as we speak, but there's several thorny issues in zero RTT that we're currently working out. So once we have numbers, we'll share them as well. Some kind of more experimental things we're exploring for future work is, and I think some of you guys have been working on this as well in various forms and flavors. So live videos uploads over Quick. So live videos are very strict. So we have a very large live video product. And so live videos have different latency requirements from HTTP downloads. They have lower latency requirements. Not very, very low, but still low latency requirements. So we're exploring what can we do with a quick transfer protocol with things like partial reliability to improve the deadlines that we give for live videos. And some of the other things is very, very low latency as well, like maybe 200, 300 millisecond range. Can we do something better for those kind of RTC kind of use cases with Quick as well? So we're open to talking about this, and we're currently exploring this right now. HTTP 3 as well. We're seeing some initial great wins, so Luca can attest to that, but we're seeing good wins with QPAC, and we're seeing that QPAC is performing as promised. And so this is great news, and we'll share numbers more when we have more data about this. Great. That's my presentation.
Thank you.
Have you been able to distinguish how often there are TCP sort of transparent proxies in the path which are affecting the TCP connections, which aren't there when you've got UDP? I mean, you can clearly you've almost certainly always got a NAT in a way, but there's the other additional little box of TCP. Can you tell the difference?
Yeah, so far we've only theorized it. We've not been able to see evidence of this. So the evidence I've been looking for at least is given a quick connection on the same network, where I've only been looking at the test script, but one of the ways we could do this is in the test script where you're using Quick on a certain network, and you know that Quick works, for example, network A, I'm not going to name any networks, but network A, and you see an RTT. And then you can see whether you're seeing a much lower RTT in the case of TCP in the control group and seeing that. However, we found that the RTT does change with Quick and TCP, so it's like kind of hard to do that, but we could explore this in the future. We haven't really looked into details. We've been mostly concentrating on like making it work. And so the 93% is like, okay, we're got it to working state. Let's get more numbers, and we'll come back to like investigating whether or not middle box is the real issues or something else is the real issue. Yeah.
Do you have any idea about the fairness of the congestion control? Really quick.
So that's another area of exploration. We've seen a few papers there which suggest that Quick's congestion control is not as fair, but we still have to explore that. We haven't really explored whether the fairness. So we don't see much of a problem because the data that we're sending is very, very small, tiny compared to data right now. But as we start sending CDN traffic and other large data content like videos, we start we will start to care more and more. We'll start to care about other things as well. For example, what is the CPU impact of Quick? So far we've not really seen much of a CPU impact of Quick from the server side. We have definitely seen a CPU impact on the client, on mobile platforms. So there's a bunch of more work to do there around CPU performance and also congestion control performance improvements.
May I just follow up on that very briefly?
Yeah.
I mean, I've also seen a bunch of papers talking about quick congestion control and how it's different from TCP congestion control.
Right.
I think it would be very useful for people doing that type of work to characterize the degrees of unfairness you get with different TCP variants.
Right.
A lot of the papers I've seen could be interpreted as suggesting that Quick is quite different to TCP, but there's also a lot of variation between the different TCP variants.
No, I don't. I think that completely makes sense, and I think that warrants a deeper study into this thing. And I'm not a congestion control expert. I do not claim to be. I don't know who claims to be that, but some people do.
You see a lot of misleading headlines, which is Quick is better or worse, whereas probably, well, there's just variation.
Exactly. It's like, for example, I don't know, I read a quote somewhere, which was like, it's not, I think it's from the RTC work, who had said, like, it's no use being fair to TCP, it won't be fair back to you. But yeah, like we do run, for example, when we do our congestion control, we run with Cubic, we run with application limited state. So one of the interesting cases around congestion control is, there was a bug in the Linux kernel for the longest time. So Cubic is time duration based. So if, for example, most of the HTTP connections are idle for most of the time, you'll see them. And so if you have sent no data, you will have nothing to lose. So the time since last loss actually goes up like cubically by the time since you're idle. So when you wake up from startup and nobody turns on slow start after idle, you will see that your congestion control is like insanely way out of whack from reality. And so this is like a bad idea generally. So recent versions of TCP or recent implementations of TCP has been implemented the idle blocking, like coming back from idle. So we do our own thing based on that, where we do it slightly differently because we know, so TCP does an approximation of what is idle based on the in-flight data and looking at the CWIN and comparing those two to each other. And so does Google Quick as well, I believe. We have a deeper, tighter integration between, since we own the HTTP layer as well as our Quick layer, a deeper, tighter integration. The HTTP layer could just tell, like, I had data outstanding, like, I had no data outstanding. I am application limited right now. Like, for example, I didn't have flow control, so I was application limited, or I didn't actually have data, so it was application limited. So maybe don't increase the flow control right now. And so what we do is we shift right whenever we wake up from the application limited stage, we shift right the Cubic congestion controller. But people are inordinately worried about Cubic. I think the more thing you should be worried about is slow start. Like, that is like not slow, and most connections we see don't exit slow start. And I think that Google has seen similar numbers in their BBR work, where BBR never exits startup like 75% of the time. So like people have been like kind of harping about like, hey, congestion controller and Cubic is bad versus this. But Cubic just remains, because the connection is idle for HTTP requests most of the time, Cubic just remains in its like kind of like a little zone of nothingness when you implement application limited. But slow start just like goes nuts. It just goes insane in the beginning of the connection. So we should do something about that rather than doing something about like Cubic.
You mentioned CPU on mobile clients. Can you speak more about that? CPU or battery life? What sort of impacts have you seen?
Yeah, so we haven't seen much impact on battery life, really, and that's like very nice because that's good. But we have seen impact on CPU on the client, where like UDP packets are slower to send, especially on older Android phones and mid-end like iOS phones. So we see like several milliseconds spent in sending UDP packet itself. Like send message takes a long time to send. So this is something that's super relevant to us so for normal HTTP requests and responses, turns out it doesn't really matter that much. Like you're already doing Java and stuff, so it probably consumes more CPU. But where it starts mattering is if you're doing video uploads over QUIC, then it starts mattering. The latency of the video uploads kind of feeds into the bandwidth estimation that you have. So we are currently seeing lower bandwidth on bandwidth uploads because of like the fact that the local time it takes to send the UV packet is like significant quantity of RTT. So we have to either, one, solve that problem somehow and change the platforms, which I don't think is, or to compensate for that in bandwidth estimation. That is, there is going to be a delay. Please compensate for that and like account for that in your bandwidth estimation algorithm. Yeah.
Briefly following up on this, you talk quite a bit about the client-facing QUIC part, but you also showed that you have this deployed on the back end.
Right.
Do you see any specific differences on what you need to do in your scaling properties of the number of endpoints you have to run and so on?
So since we're running, even on the backend side, since we're running API traffic, we actually haven't seen any noticeable difference in CPU even on the backend side. But I think we will start seeing it once we do CDN traffic and other like long form concept on. The other property, which is less interesting in the backend, so I've not spent a bunch of time in the backend because potentially it's less interesting because the loss rate is almost zero. We don't lose many packets on our backbone, so it's a good backbone. It's very nice. The best. Potentially, basically, we see wins on 0 RTT. So we see wins in the 1 RTT connection setup. We're not running TL 0 RTT on the backbone for various reasons, and so we see wins on connection setup time in cases where there are a lot of different websites fronting. Like Facebook has a lot of different websites which are fronted by the same load balancer, which is Proxygen, Edge and Origin load balancers is Proxygen. There are different levels of connection pooling and different levels of connection reuse rate. So QUIC helps with the connection. If your connection reuse rate is low, or you're running a very less frequently used website, then that's actually, it will be a win for you. And we see wins there at that point, the backend load balancer side of things. We don't see wins from loss recovery or anything of sort. We see wins only in the connection setup time.
Okay. Because you also run probably the backend connections in a different regime, right? You don't, if you aggregate, then I don't know whether you aggregate, but if you would aggregate, then you wouldn't see idle periods on the backend.
So we do that. For example, we have. Sorry, Luca, you want to answer?
Okay. From Edge to Origin, we have like 99% connection reuse. So even if you do 0 RTT, it's like a marginal win.
Yeah. So
it's not worth the effort.
Yeah, for some that is for the frequently used ones, but there are some of them which have like very low traffic, and like they see wins because they're like, oh yeah, even if you aggregate them, if you get like 5 RPS, you're not, how much connection reuse can you really do? Yeah, so how much aggregation will really help?
I have a question about the Proxygen. So, what is the scale of the connections that a Proxygen might be handling at any time?
So I wish I could reveal the number, but you're asking about number of connections per second.
Even order of magnitude.
Oh yeah, I mean there's connections. I don't recall, but we have shared this other number, so I can probably say this. So we process like trillions of requests a day. So I can say this because we reveal that number. I don't know for a fact whether we have revealed the number of connections per second, so I'm not sure whether I can say that in the moment. We can follow up offline if you want to. Yeah, so it's a very large service, and it per host it processes a lot of connections, a lot of requests per host.
Yes, and I've heard lots of huge numbers there.
Yeah.
So yeah, we should follow up on that.
Sounds good.
You talked about various components of your system being open source, and I think MoveFast will be open source, or is open source, or what's the plan?
It's not yet open source, but we'll make it open source. Yeah, it will be open source soon. Yeah. Soon, as in, not promising a timeline, but soon.
Hey, you can do a demo in Beijing if you've open sourced it, but get it out, Beijing. All right.
Will both the client and the server implementation be open source?
Yeah, they're pretty much the same. So same library.
So I think we are almost holding on a coffee break.
Go.
I wonder about the design of reusing the connection ID to put in different things. On the one hand, it's very flexible, it's very nice, you can just use it for routing. On the other hand, you can use a lot of semantics. It's not only the connection ID, it's got all these other things routed in. I know it's part of the design, it's really intended for that use, but it still feels a bit dirty, that there's not a separate field for routing, and that's maybe because then you will get complaints that you're now also subsuming layer 3.
Yeah, I mean, I guess connection ID is kind of like the new addressing, right? It's like your IPv6 address for which you can put stuff into. I think there's some work going on in, I don't think we'll be accused of being ugly because there's some work going on in the IP layer as well to put information and add assigned addresses. For example, I've been following the ILA work, which embeds, basically you can have a structure around your IP address and put bits in there to denote various other properties and qualities of the host. So yeah, I just think it's a more flexible. It is not bound to routing, so it's not bound to routing in your in a BGP sense of the way, but it is a routing token where you can just have extra information to where networks presumably will not look at the data and help you in routing the packets the right way. Hopefully, the networks will not look at the data and route you the right way. No, I think you should go this way, actually.
So, but there's this assumption, right, that you could control both sides. So you know, PicoQuick wouldn't necessarily embed that information. Well, not server generated. Sorry, forget.
Right. It's unilateral. Yeah, so the feature of server generated connection ID is that you can actually the peer does not need to understand what your format is. And so you can generate, it's just an opaque string to the peer, opaque length as well. So you don't even, a middle box, once a connection is established, a middle box cannot know what the length of the connection ID is. So that's also another feature of the design.
All right. Thanks a lot.
Thank you again.